Chapter 12 Linear Programming. Introduction. In earlier classes, we have discussed the systems of linear equations and their applications in day-to-day problems. A furniture dealer deals in only two items, tables and chairs. He has rupees 50,000 to invest and has storage space of at most 60 pieces. A table cost rupees 2,500 and a chair rupees 500. He estimates that from the sale of one table, he can make a profit of rupees 250 and that from the sale of one chair a profit of rupees 75. He wants to know how many tables and chairs he should buy from the available money so as to maximize his total profit, assuming that he can sell all the items which he buys. Such type of problems which seek to maximize or minimize profit or cost form a general class of problems called optimization problems. Thus, an optimization problem may involve finding maximum profit, minimum cost, or minimum use of resources, etc. A special but a very important class of optimization problems is linear programming problem. The above stated optimization problem is an example of linear programming problem. Linear programming problems are of much interest because of their wide applicability in industry, commerce, management science, etc. Linear programming problem and its mathematical formulation. We begin our discussion with the above example of furniture dealer, which will further lead to a mathematical formulation of the problem in two variables. In this example, we observe number 1, the dealer can invest his money in buying tables or chairs or combination thereof. Further, he would earn different profits by following different investment strategies. Number 2, there are certain overriding conditions or constraints, namely his investment is limited to a maximum of rupees 50,000 and so is his storage space, which is for a maximum of 60 pieces. Suppose he decides to buy tables only and no chairs, so he can buy 50,000 divided by 2,500, that is 20 tables. His profit in this case will be rupees 250 into 20, that is rupees 5,000. Suppose he chooses to buy chairs only and no tables with his capital of rupees 50,000. He can buy 50,000 divided by 500, that is 100 chairs. But he can store only 60 pieces. Therefore, he is forced to buy only 60 chairs, which will give him a total profit of rupees 60 into 75, that is rupees 4,500. There are many other possibilities. For instance, he may choose to buy 10 tables and 50 chairs. As he can store only 60 pieces, total profit in this case would be rupees 10 into 250 plus 50 into 75, that is rupees 6,250, and so on. We thus find that the dealer can invest his money in different ways and he would earn different profits by following different investment strategies. Mathematical formulation of the problem. Let x be the number of tables and y be the number of chairs. Then the dealer buys. Obviously, x and y must be non-negative. That is, x is greater than or equal to 0. Non-negative constants. Equation 1. Y is greater than or equal to 0. Equation 2. The dealer is constrained by the maximum amount he can invest. Here it is rupees 50,000, and by the maximum number of items he can store. Here it is 60. Stated mathematically, 2,500x plus 500y is less than or equal to 50,000. which is investment constraint. Or 5x plus y is less than or equal to 100, equation 3, and x plus y is less than or equal to 60, which is storage constraint, equation 4. The dealer wants to invest in such a way so as to maximize his profit, say z, which stated as a function of x and y is given by z is equal to 250x plus 75y, called objective function, equation 5. Mathematically, the given problems now reduces to maximize z is equal to 250x plus 75y, subject to the constraints 5x plus y is less than or equal to 100, x plus y is less than or equal to 60, x is greater than or equal to 0, y is greater than or equal to 0. So, we have to maximize the linear function z subject to certain conditions determined by a set of linear inequalities with variables as non-negative. There are also some other problems where we have to minimize a linear function subject to certain conditions determined by a set of linear inequalities with variables as non-negative. Such problems are called linear programming problems. Thus, a linear programming problem is one that is concerned with finding the optimal value, that is maximum or minimum value of a linear function called objective function of several variables, say x and y, subject to the conditions that the variables are non-negative and satisfy a set of linear inequalities called linear constraints. The term linear implies that all the mathematical relations used in the problem are linear relations, while the term programming refers to the method of determining a particular program or plan of action. Objective function. Linear function z is equal to ax plus by, where a, b are constants which has to be maximized or minimized is called a linear objective function. In the above example, z is equal to 250x plus 75y is a linear objective function. Variables x and y are called decision variables. Constraints. The linear inequalities or equations or restrictions on the variables of a linear programming problem are called constraints. The conditions x is greater than or equal to 0, y is greater than or equal to 0 are called non-negative restrictions. In the above example, the set of inequalities 1 to 4 are constraints. Optimization problem. A problem which seeks to maximize or minimize a linear function, say of two variables x and y, subject to certain constraints as determined by a set of linear inequalities is called an optimization problem. Linear programming problems are special type of optimization problems. Graphical method of solving linear programming problems. Let us refer to the problem of investment in tables and chairs discussed in previous section. We will now solve this problem graphically. Let us graph the constraints stated as linear inequalities. 5x plus y is less than or equal to 100. Equation 1. X plus y is less than or equal to 60. Equation 2. X is greater than or equal to 0. Equation 3. Y is greater than or equal to 0. Equation 4. The graph of this system, that is shaded region, consists of the points common to all half planes determined by the inequalities 1 to 4. Each point in this region represents a feasible choice open to the dealer for investing in tables and chairs. The region, therefore, is called the feasible region for the problem. Every point of this region is called a feasible solution to the problem. Thus, we have feasible region, the common region determined by all the constraints, including non-negative constraints. X, y is greater than or equal to 0 of a linear programming problem is called the feasible region or solution region for the problem. In figure, the region OABC, which is shaded, is the feasible region for the problem. The region other than feasible region is called an infeasible region. Feasible solutions. Points within and on the boundary of the feasible region represent feasible solutions of the constraints. In figure, every point within and on the boundary of the feasible region OABC represents feasible solution to the problem. For example, the point 10, 50 is a feasible solution of the problem, and so are the points 0, 60, 20, 0, etc. Any point outside the feasible region is called an infeasible solution. For example, the point 25, 40 is an infeasible solution of the problem. Optimal, that is feasible solution. Any point in the feasible region that gives the optimal value, which is maximum or minimum, of the objective function is called an optimal solution. Now, we see that every point in the feasible region OABC satisfies all the constraints as given in equation 1 to 4. And since there are infinitely many points, it is not evident how we should go about finding a point that gives a maximum value of the objective function z is equal to 250x plus 75y. Theorem 1. Let R be the feasible region which is convex polygon for a linear programming problem, and let z is equal to ax plus by be the objective function when z has an optimal value, which is maximum or minimum, where the variables x and y are subject to constraints described by linear inequalities. This optimal value must occur at a corner point, that is vertex of the feasible region. Theorem 2. Let R be the feasible region for a linear programming problem, and let z is equal to ax plus by be the objective function. If R is bounded, then the objective function z has both a maximum and a minimum value on R, and each of these occurs at a corner point, that is vertex of R. Remark. In the above example, the corner points, that is vertices of the bounded, that is feasible region are O, A, B and C, and it is easy to find their coordinates as 0, 0, 20, 0, 10, 50 and 0, 60 respectively. Let us now compute the value of z at these points. A corner point of a feasible region is a point in the region which is the intersection of two boundary lines. A feasible region of a system of linear inequalities is said to be bounded if it can be enclosed within a circle. Otherwise, it is called unbounded. Unbounded means that the feasible region does extend indefinitely in any direction. Vertex of the feasible region, which is O, 0, 0, A, 0, 60, B, 10, 50, C, 20, 0. Corresponding value of z in rupees, which is 0, 4,500, 6,250, which is maximum 5,000. We observe that the maximum profit to the dealer results from the investment strategy 10-50, that is buying 10 tables and 50 chairs. This method of solving linear programming problem is referred as corner point method. The method comprises of the following steps. Number 1. Find the feasible region of the linear programming problem and determine its corner points, that is vertices, either by inspection or by solving the two equations of the lines intersecting at that point. Number 2. Evaluate the objective function z is equal to ax plus by at each corner point. Let capital M and small m respectively denote the largest and smallest values of these points. Number 3. In number 1, when the feasible region is bounded, capital M and small m are the maximum and minimum values of Z. Number 2. In case the feasible region is unbounded, we have number 4. In A, capital M is the maximum value of Z if the open half plane determined by AX plus BY is greater than M, has no point in common with the feasible region, otherwise Z has no maximum value. B. Similarly, small m is the minimum value of Z if the open half plane determined by AX plus BY is less than M, has no point in common with the feasible region, otherwise Z has no minimum value. Here are some examples using the vertex method. Example 1. Solve the following linear programming problem graphically. Maximize Z is equal to 3x plus 4y. Subject to constants x plus y is less than or equal to 4, x is greater than or equal to 0, y is greater than or equal to 0. Solution: x is greater than or equal to 0, y is greater than or equal to 0. Implies the values of x and y are in the first quadrant. X plus y is less than or equal to 4, x plus y is equal to 4. Implies x upon 4 plus y upon 4 is equal to 1. Implies the line intersects x-axis at A 4, 0 and y-axis at B 0, 4. Joining points A and B, we get the line x plus y is equal to 4. 4, 0, 0. 0 plus 0 is less than or equal to 4, which is true. Therefore, the half plane containing the origin 0, 0 is the feasible region of the inequality x plus y is less than or equal to 4. Now, shaded region OAB is the feasible region of the given linear programming problem. It is bounded region. Its corner points are O, 0, 0, A, 4, 0 and 0, 4. Corner point which is O, 0, 0, A, 4, 0, B, 0, 4. Corresponding value of Z is equal to 3x plus 4y, which is Z is equal to 0, Z is equal to 12, Z is equal to 16. The maximum value of Z is equal to 3x plus 4y is 16 at a point B, 0, 4. Example 2. Find minimize Z is equal to minus 3x plus 4y subject to x plus 2y is less than or equal to 8. 3x plus 2y is less than or equal to 12. X is greater than or equal to 0. Y is greater than or equal to 0. Solution: x is greater than or equal to 0. Y is greater than or equal to 0. Implies the values of x and y are in the first quadrant. X plus 2y is less than or equal to 8. X plus 2y is equal to 8 implies x upon 8 plus y upon 4 is equal to 1. Implies the line intersects x-axis at A 8, 0 and the y-axis at B 0, 4. 4, 0, 0. 0 plus 0 is less than or equal to 8, which is true. Therefore, x plus 2y is less than or equal to 8 shows the half plane containing the origin O 0, 0. 3x plus 2y is less than or equal to 12. 3x plus 2y is equal to 12 implies x upon 4 plus y upon 6 is equal to 1. Implies the line intersect x-axis at A dash 4, 0 and y-axis at B dash 0, 6. 4, 0, 0. 0 plus 0 is less than or equal to 12, which is true. Therefore, half plane containing 0, 0 is the region of 3x plus 2y is less than or equal to 12. The feasible region is the solution set which is shaded region and is OA-PB in the graph. Corner point which is O, 0, 0, A-4, 0, P, 2, 3, B, 0.04. Corresponding value of z is equal to minus 3x plus 4y, which is z is equal to 0, z is equal to minus 12, z is equal to 6, z is equal to 16. Hence, the minimum value of z is equal to minus 3x plus 4y is minus 12 at the point 4, 0. Example 3. Find maximize z is equal to 5x plus 3y. Subject to 3x plus 5y is less than or equal to 15. 5x plus 2y is less than or equal to 10. X is greater than or equal to 0. Y is greater than or equal to 0. Solution: x is greater than or equal to 0. Y is greater than or equal to 0. Implies the values of x and y are in first quadrant. 3x plus 5y is less than or equal to 15. 3x plus 5y is equal to 15 implies x upon 5 plus y upon 3 is equal to 1. Implies the line intersects the x-axis at A, 5, 0 and y-axis at B, 0, 3. 3x plus 5y is equal to 15 is a line joining the points A, 5, 0 and B, 0, 3. 4, 0, 0. 0 plus 0 is less than or equal to 15, which is true. Therefore, the half plane of 3x plus 5y is equal to 15 containing 0, 0 shows the solution region of 3x plus 5y is less than or equal to 15. 5x plus 2y is less than or equal to 10. 5x plus 2y is equal to 10. Implies x upon 2 plus y upon 5 is equal to 1. The line 5x plus 2y is equal to 10 intersects the x-axis at A dash 2, 0 and y-axis at B dash 0, 5. 5x plus 2y is less than or equal to 10 is a line joining the points A dash 2, 0 and B dash 0, 5. 4, 0, 0. 0 plus 0 is less than or equal to 10, which is true. Therefore, the half plane containing 0, 0 shows the solution region of 5x plus 2y is less than or equal to 10. Hence, the feasible region of the given linear programming is OA-PB, which is shown as shaded region in graph. By solving the equation 3x plus 5y is equal to 15 and 5x plus 2y is equal to 10, we get the coordinates of the point P. Therefore, x upon determinant 5 minus 15, 2 minus 0 is equal to y upon determinant minus 15, 3 minus 10, 5 is equal to x upon determinant 3, 3, 5, 2. Implies x is equal to 20 upon 19, y is equal to 45 upon 19. Therefore, the coordinates of P is equal to 20 upon 19, 45 upon 19. Therefore, the corner points of the feasible region are O, 0, 0, A dash, 2, 0, P, 20 upon 19, 45 upon 19 and B, 0, 3. Corner point which is O, 0, 0, A dash, 2, 0, P, 20 upon 19, 45 upon 19, B, 0, 3. Corresponding value of z is equal to minus 3x plus 4y, which is z is equal to 0, z is equal to 10, z is equal to 235 upon 19, z is equal to 9. Hence, the maximum value of z is equal to 5x plus 3y is 235 upon 19 at a point P, 20 upon 19, 45 upon 19. Different types of linear programming problems. Number 1. Manufacturing problems. In these problems, we determine the number of units of different products which should be produced and sold by a firm when each product requires a fixed manpower, machine hours, labor hour per unit of product, warehouse space per unit of the output, etc. in order to make maximum profit. Number 2. Diet problems. In these problems, we determine the amount of different kinds of constituents or nutrients which should be included in a diet so as to minimize the cost of the desired diet such that it contains a certain minimum amount of each constituent or nutrients. Number 3. Transportation problems. In these problems, we determine a transportation schedule in order to find the cheapest way of transporting a product from plants or factories situated at different locations to different markets. Example 1. Reshma wishes to mix two types of food, P and Q, such a way that the vitamin contents of the mixture contain at least 8 units of vitamin A and 11 units of vitamin B. Food P cost rupees 60 per kilogram and food Q cost rupees 80 per kilogram. Food P contains 3 units per kilogram of vitamin A and 5 units per kilogram of vitamin B, while food Q contains 4 units per kilogram of vitamin A and 2 units per kilogram of vitamin B. Determine the minimum cost of the mixture. Solution. Let food P consist of X kilogram and food Q consist of Y kilogram. We make the following table from the given data. Resources: vitamin A, type of food, P 3 units, Q 4 units. Requirement: at least 8 units. Resources: vitamin B, type of food, P 5 units, Q 2 units. Requirement: at least 11 units. Cost: rupees per kilogram. Type of food, P rupees 60, Q rupees 80. We have constraints: X is greater than or equal to 0, Y is greater than or equal to 0. Equation 1. 3x plus 4y is greater than or equal to 8. Equation 2. 5x plus 2y is greater than or equal to 11. Equation 3. Z is equal to 60x plus 80y. We have to find the minimum value of Z. Let us graph the inequalities 1, 2 and 3. The feasible region determined by the system is shown in the graph. It is unbounded region. The corner points are A 0, 5.5, B 2, 1 upon 2 and C 8 upon 3, 0. Corner point which is A 0, 5.5, B 2, 1 upon 2, C 8 upon 3, 0. Corresponding value of Z is equal to 60x plus 80y, which is Z is equal to 440, Z is equal to 160, Z is equal to 160. The minimum value of Z is 160. It is at all the points of the line segment joining the points B 2, 1 upon 2 and C 8 upon 3, 0. It is clear that there is no common points of the open half plane 60x plus 80y less than 160 with the feasible region. Hence, the minimum cost of the mixture is rupees 160. Example 2. Allocation problem. A cooperative society of farmers has 50 hectares of land for growth to crops X and Y. The profit from crops X and Y per hectare are estimated as rupees 10,500 and rupees 9,000 respectively. To control weeds, a liquid herbicide has to be used for crops X and Y at rates of 20 liters and 10 liters per hectare. Further, no more than 800 liters of herbicide should be used in order to protect fish and wildlife using a pond which collects drainage from this land. How much land should be allocated to each crop so as to maximize the total profit of the society? Solution. Let X hectare of land be allocated for crop X and Y hectare to crop Y. Obviously, X is greater than or equal to 0, Y is greater than or equal to 0. Profit per hectare on crop X is equal to rupees 10,500. Profit per hectare on crop Y is equal to rupees 9,000. Therefore, total profit is equal to rupees 10,500 X plus 9,000 Y. The mathematical formulation of the problem is as follows. Maximize Z is equal to 10,500 X plus 9,000 Y. Subject to the constraints, X plus Y is less than or equal to 50. Constraint related to land, equation 1. 20x plus 10y is less than or equal to 800. Constraint related to use of herbicide, that is 2x plus y is less than or equal to 80. Equation 2. X is greater than or equal to 0, y is greater than or equal to 0. Non-negative constraint. Equation 3. Let us draw the graph of the system of inequalities 1 to 3. The feasible region OABC is shown region which is shaded in the figure. Observe that the feasible region is bounded. The coordinates of the corner points O, A, B and C are 0, 0, 40, 0, 30, 20 and 0, 50 respectively. Let us evaluate the objective function Z is equal to 10,500 X plus 9,000 Y at these vertices to find which one gives the maximum profit. Corner point which is O 0, 0, A 40, 0, B 30, 20, C 0, 50. Corresponding value of Z is equal to 10,500 X plus 9,000 Y, which is 0, 4,20,000, 4,95,000, maximum 4,50,000. Hence, the society will get the maximum profit of rupees 4,95,000 by allocating 30 hectares for crop X and 20 hectares for crop Y. Example 3. A factory manufactures two types of screws, A and B. Each type of screw requires the use of two machines, an automatic and a hand-operated. It takes 4 minutes on the automatic and 6 minutes on hand-operated machines to manufacture a package of screws A, while it takes 6 minutes on automatic and 3 minutes on the hand-operated machines to manufacture a package of screws B. Each machine is available for at the most 4 hours on any day. The manufacturer can sell a package of screws A at a profit of rupees 7 and screws B at a profit of rupees 10. Assuming that he can sell all the screws he manufactures, how many packages of each type should the factory owner produce in a day in order to maximize his profit? Determine the maximum profit. Solution. We make the following table from the given data. Types of machine. Automatic. Types of screws. P 4 minutes. Q 6 minutes. At the most time, 4 hours is equal to 240 minutes. Types of machine hand operated. Types of screws. P 6 minutes. Q 2 minutes. At the most time, 4 hours is equal to 240 minutes. Types of machine. Profit. Types of screws. P rupees 7. Q rupees 10. Let the factory owner produce X packages of screw A and Y packages of screw B in a day. Maximize Z is equal to 7x plus 10y subject to the constraints 4x plus 6y is less than or equal to 240 implies 2x plus 3y less than or equal to 120. Equation 1. 6x plus 3y is less than or equal to 240 implies 2x plus y is less than or equal to 80. Equation 2. X is greater than or equal to 0. Y is greater than or equal to 0. Equation 3. Let us draw the graph of the system of inequalities 1, 2 and 3. The feasible region is OABC. It is shown in the figure by shaded region. It is bounded region. Its corner points are O, 0, 0, A, 40, 0, B, 30, 20 and C, 0, 40. Corner point, which is O, 0, 0, A, 40, 0, B, 30, 20, C, 0, 40. Corresponding value of Z is equal to 7x plus 10y, which is Z is equal to 0, Z is equal to 280, Z is equal to 410, Z is equal to 410, Z is equal to 400. The maximum value of Z is equal to 7x plus 10y is rupees 410 at B 30, 20. Thus, if the manufacturer produces 30 screws of type A and 20 screws of type B, he earns a maximum profit of rupees 400